We can use molecular orbital theory to explain many phenomena. One example is the octet rule. It says that the atoms of light main group elements tend to combine in such a way that each atom has 8 electrons in its valence shell, including the shared electrons. Here, light means the elements are in the second and third periods. Main groups are the groups in the S and P blocks in the periodic table. The octet rule is valid for elements from carbon to argon and occasionally applicable to some other elements. For example, a carbon atom bonds with 4 hydrogen atoms to form methane. The carbon atom has 8 electrons in its valence shell. Another example is sodium fluoride, which is an ionic compound. Pay attention that sodium atom has only 1 electron in its valence shell, M shell. When it loses 1 electron, the valence shell of the sodium cation becomes the L shell. However, if the valence shell has only s orbital, it needs only 2 electrons to stabilize. It is the duet rule. The duet rule applies to hydrogen anion, helium atom and lithium cation. Boron is a very special element. A boron atom has only 3 electrons in its valence shell. Its electronegativity does not allow it to lose all its valence electrons to comply duet rule. In a molecule with boron atoms, they have covalent bond with other atoms. Each boron atom can have 6 valence electrons. Typical examples are borane and boron trifluoride. Such compounds are relatively stable. They do not decompose by themselves, but they are active in reaction with other substances. Some boron compounds are even stranger, which cannot be explained by valence bond theory at all. For example, the boron-12 molecule. Each boron atom bond with 5 other boron atoms. Even so, it only has 3 electrons in its valence shell. In the diborane molecule, 2 hydrogen atoms form bridges between the 2 boron atoms. It is not a typical behavior of hydrogen atoms, because they prefer to locate at the terminals. In general chemistry, we will not discuss the details of the bondings in boron-12 and diborane molecules. The only thing you need to be aware is that they do not comply the octet rule. There are boron compounds which comply the octet rule, and they are indeed more stable. You can check the examples of tetrahydroborate, tetrafluoroborate and tetrahydroxyborate anions. Atoms in and after the third period can accommodate more than 8 electrons in their valence shell because the existence of the d orbitals. In the antimony pentafluoride molecule, the antimony atom forms 5 single bonds with the fluorine atoms. As a result, it has 10 valence electrons. Similarly, in the triiodide anion, the central iodine atom has 10 valence electrons. For transition metals, there is an 18-electron rule. The theoretical basis of the 18-electron rule is that the valence shell of a transition metal atom is composed of d, s and p orbitals. When they are occupied by 18 electrons, the system is most stabilized. Here, I use carbonyl compounds of cobalt and nickel as examples. In carbonyl compounds, each carbonyl group donates 2 electrons to the central atom via a coordinate covalent bond, and the number of valence electrons of the metal is increased by 2. The numbers of valence electrons of cobalt and nickel atoms in isolation are 9 and 10 respectively. The nickel atom in nickel tetracarbonyl molecule has 18 valence electrons, so it is stable. The cobalt atom in cobalt tetracarbonyl molecule has 17 valence electrons, so it is unstable. If the unstable cobalt tetracarbonyl molecule accepts an electron, the cobalt atom will have 18 valence electrons, so the cobalt tetracarbonyl anion is stable. Another way to form a stable system from cobalt tetracarbonyl is to form dicobalt octacarbonyl molecule. The 2 cobalt atoms form a single bond to share a pair of electrons. Thus, each cobalt atom has 18 valence electrons, and the molecule is stable. Sometimes, when writing the Lewis structures, there are non-identical structures which are equivalent to each other. This phenomenon is called resonance. Pay attention, this resonance is a different concept from the resonance in oscillation. The non-identical but equivalent structures are called contributors. For example, when writing the Lewis structure of nitrate ion, the double bond can be between the nitrogen atom and any one of the 3 oxygen atoms. Those Lewis structures are non-identical but equivalent. You may think that there is a mixture of contributors, or the system converts from one contributor to another over time. But they are not true. The individual contributors are never observed by experiments. Thus, the resonance is not a mixing or conversion of contributors. The molecule or ion in with resonance actually has only one structure. For example, in the Lewis structure of nitrate ion, there are two types of nitrogen-oxygen bonds. But from experimental result, nitrate ion has only one structure. All the nitrogen-oxygen bonds are identical. Resonance reflexes the delocalization of electrons. As we have discussed before, some molecular orbitals are formed by the combination of more than two atomic orbitals. In the nitrate ion, the nitrogen atom is sp2 hybridized. Each of the sp2 hybridized orbital form a sigma bond with one oxygen atom. The 2pz orbital of nitrogen is perpendicular to the molecular plane, as well as the 2pz orbitals of oxygen atoms. They form delocalized molecular orbitals. The formation of molecular orbitals from atomic orbitals in nitrate ion is shown here. The coefficients are calculated with group theory. You don't need to understand the details, but you should notice that the molecular orbitals are delocalized. The delocalization of orbital and electrons is responsible for many special properties of aromatic molecules and conjugated hydrocarbons. For example, the Lewis structures of benzene have two contributors, but the experiments show that benzene has only one structure, which is regular hexagon. The carbon atoms are sp2 hybridized. The sp2 hybridized orbitals of a carbon atom form three sigma bonds with a hydrogen atom and two neighboring carbon atoms. The 2pz orbitals of carbon atoms form delocalized pi orbitals. In the pi orbitals, the electrons are shared by all the carbon atoms. They can be represented by a ring. The molecular orbital diagram of benzene from the 2pz orbitals is shown below. There are 3 bonding orbitals and 3 antibonding orbitals. There are 6 electrons in those orbitals. In the ground state, all electrons are in the bonding orbitals, so that benzene molecule is stabilized. In conjugated hydrocarbons, alternative single and double bonds in their Lewis structures are actually delocalized electrons. They are free to move in the delocalized molecular orbitals. Thus, conjugated hydrocarbons are conductive.